This talk is data-oriented architectures. Can everyone hear me fine there? Awesome. So I'm Norbert. I go by that nickname everyone on the internet. I gave a talk last year at Lambda Days about ClojureScript, just for my own personal curiosity. Has anybody seen it? Okay, a couple hands will go up. And you've decided to come back for another talk. Why? This is going to be a different talk because I want to talk about system design and system architecture. So we're going to be up in the clouds, but not up in space, right? So still pragmatic, but architecture, not code. Which is important because if you are interested in looking at code and so forth, you should probably go to one of the other talks. We won't have any code here, and on top of that, none of the ideas that I present are innovative in the sense that they're not my ideas. They're things that have been around for a while, but for some reason they're not getting as much attention as they should. So this is why we have this talk. Anybody who knows me personally knows that I have very strong opinions and I'm not afraid to share them with everyone. So this talk is just one person's idea of how to build systems. Take from it what you may. I want to give you a little background about myself so you have a little context about where I'm coming from. I build stuff in various industries, including business, sports, non-emergency health devices, booking hotels, booking flights, et cetera, et cetera. Lots of different industries, but basically always the same thing. Some kind of highly available internet-based backend with distributed clients, whether they're mobile or web or some other kinds of devices. All these companies, for some reason, call themselves product companies. Some are B2C, some are B2B. The only thing that I can figure out that all of these things share in common is that they have some notion that user interface is important and that user interface is important, right? User experience. I am not a particular fan of this term. I like to think of them as information systems. So the way I define it is that the main primary purpose in life of an information system is to serve as this black box where data comes in that's external from the system. So users provide data or other machines provide data. We store it securely. And then at some point later in the future, someone comes and asks it questions, and we give it answers and insights, and et cetera, et cetera. So just to get a feeling for the audience, who here has worked on something like an information system? Pretty much everyone raises their hands, because if you haven't, you're either working in building compilers, or you're doing real-time embedded systems, or you're working on your PhD, I presume. Okay, but how many of you had suffered the burden of technical debt? Same exact hands go up. Functional programming. Who here is excited about functional programming? This is Lambda Days. This is a trick question. But how many of you tried to teach it to your colleagues and failed? Yeah. So this talk is a silver bullet. And the reason this talk is a silver bullet is that it turns out I can solve both of those seemingly unrelated problems for you. Now, I know that makes me sound like a crazy person. But before you judge, let me also tell you that I believe in a conspiracy theory. And the conspiracy theory is the following. We have model view controllers, service-oriented architectures, don't repeat yourself, and test-driven development. All suspiciously three-letter acronyms, and all, I believe, are slowly but surely killing and poisoning your projects. I believe they are the snake oil salesmen of the software industry because they consistently overpromise while consistently under-delivering, and worst of all, giving you a false sense of security that what you're building makes sense until it's far too late to change it. Take, for example, encapsulation, right? It's a beautiful idea. It's this idea that I like to think of this as the complexity iceberg. All business domains, whatever you're working on, are essentially a complexity iceberg because it turns out that in the real world, things are messy and difficult and complicated. And so the way we deal with it, ideally, is that we build this iceberg where we push all the details underneath the water where we don't need to think about it on a daily basis, right? Because things should sort of just be working out on their own. You solve the problem once, and then you no longer have to think about it. You have this nice API or some kind of facade up on top that you deal with on a daily basis. The question is, how do these solutions attack this problem? So MVC, for example, is this idea that this system that we've been building has become complex. Why has it become complex? A consultant comes along and says, the reason why it's complex is I see these things that are models and these things that are views, and they should be independent of each other. So the consultants come in they separate the things into models, views, and controllers. They pat themselves on the back, and they go home. 6 months later, you're on the floor sobbing because somehow the complexity didn't go away. They didn't solve anything. This talk is far too short for me to tell you horror stories about MVC, but I'm sure you've all discovered them. I know you've discovered them because we invented service-oriented architectures, right? This was somehow magically supposed to solve the problems that we had with these monolithic MVC applications. What was the idea? The idea was that those same consultants came back and said, no, 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 no. The problem is that you have this big monolith and you need to split it into multiple things that do one thing and one thing well. How did it work? How does this work in practice, though? In reality, what happens is now you have multiple problems. You had one MVC, and now you have 4 MVCs. So you have 4 problems instead of 1. And on top of that, it turns out that no matter how you model these services, it turns out that all of these things are interdependent on each other. I've never seen a system implemented in such a way that you can ask one of these services a question and it doesn't need to start chatting to all the other services in order to give you a sensible response, right? The separation is on the wrong level. We had an architectural problem and we tried to solve it with some kind of quick fix technical solution. We wanted to create a complexity iceberg for ourselves, and instead we created a dependency iceberg, where there was this huge oil spill, and then we just started pushing things on the bottom and hoping, God forbid, we never have to dive and fix things all the way over there. Same thing with duplication, right? Don't repeat yourself. Deduplicate code. I keep seeing this everywhere, but this was never the idea behind DRY. The idea behind DRY was that you had a single source of truth, right? This was the idea, that if there's a bit of information in your system, you need to store it in one place so you know everything that depends on it and you can change it in that one place. But this is not how it ever happens in real life. In real life, this is especially a sin committed by object-oriented programmers. They create abstract factories and classes, or even worse, they create mix-ins that bring in dependencies at runtime. So you can't even see it in the static code. You see it at runtime. They tried to hack around with a technical solution, and all they did was they created more coupling in your system. Same thing can be said about reliability and testing. Because I think if you ask anybody over a beer, I think they're going to tell you that testing is about having reliable systems. I like to think of it as confidence, though. I like to think of it as the idea that I want testing to improve the confidence I have in my code base, that it runs correctly, and that the thing that I'm building is the thing I'm supposed to be building. This is what really irks me about test-driven development, though, and the people who are behind it. They're really pro-unit testing, but if the goal is confidence, why are we ignoring all these other things? Types and schemas are really useful, and so are runtime assertions. Why is it that Erlang can do it and nobody else can? What about generative property testing? These are all kinds of things that improve our confidence in our code, but for some reason we ignore it as a community. Right? A lot of the kinds of unit tests that I see are things that are usually solved by types, schemas, or property testing. Again, unit tests were easy, so it was a quick technical fix, but it didn't really solve the problem that we were trying to improve the confidence. And on top of that, unit tests, the way we write them in the industry, they just create lots and lots of coupling in our system. I know I'm being just a little melodramatic here. I know that these are just tools, and that they're not the end of the world. But the real problem is that people forget that these things are tools. They start treating them like religion. And these are where the problems come in. Because when you start treating things as religion, you stop realizing that things can be different and you can do things in different ways. Because if we're going to talk about religion, I have to just admit to you that I'm a devout Rich Hickey convert. I believe in the almighty power of data and queues and the concurrency fairy. Unfortunately, concurrency fairy isn't real. All you've got left is data and queues. Projects fail. Projects fail all of the time. I think it's for one of 3 reasons. You don't understand the domain, so you build the wrong thing. Or you don't actually model the domain, so you end up building the wrong thing. Or inevitably, somewhere down the line, you break rules 1 or 2, and you're unwilling or unable to adapt and change. So I've been doing some soul searching. And I said, we need to build things in a better way. And in order to figure out what is the better way, we need to define some principles. So I made up 2 guiding principles for myself. Whatever I decide, I should strive to model the essence of things. I'm not promising myself that I'm going to be able to manage this, but whatever we do, we should at least strive to model the essence of things and try not to violate physics. I think these are 2 really good guiding principles. So whenever we hit an architectural decision where there's one of 2 ways we can go down, which roads, we should come back to these principles and see which one fits these rules that we made up for ourselves. And so this is the moment in the talk where I can tell you my slash dot inspired recipe for success. So this is what's going to help us build real nice systems. We have data, flow, magic sauce, and profit. Data. We got to have some rules. Data must be immutable. And not because it's cool and it's what all the hipster kids are doing, but because that's how the real world works. In the real world, all data information is immutable, right? Just by definition. We are very simple-minded people in the sense that we don't understand multiverse theory and parallel universes and Schrodinger's equations and so forth. As far as we understand, things are. And things may change over time, but when I say that something is something at a certain point in time, nobody goes and says, no, maybe it isn't, right? Because that's essentially what mutation is. You don't want to explain to your users that your system supports Schrodinger data. You just don't. Avoid this subject at all costs. And the way you do it is you just have immutable data. The data must have certain semantics. So since we're striving to model the essence of things, we're going to limit the number of primitives that we use. And the way we're going to decide on this is that we're going to talk about semantics. If there's 2 things in our system, there must be a reason why these 2 things exist. And the reason these 2 things exist is they have different semantics. Because if they had the same semantic, then we could just model it with one thing. And because we're limiting the number of kinds of things that we're going to be using, we need recursion. Because recursion will let us now build up once again from primitives to complex models. So this is really abstract, but I want to give you some concrete examples. Kinds of things that are primitive are, for example, scalars. Things like strings, booleans, numbers, nil. Another useful attribute to model is the idea of identity. I really like the fact that in Clojure there are 2 forms of identity, symbols and keywords. And Clojure APIs really take advantage of this fact because you can then apply completely different semantics to what it means for something to be identified by a symbol or a keyword. You have collections, lists, maps, vectors, sets. All have very different semantics and all support recursion. And sometimes in your domain, you have custom things, right? For example, that thing up on top is a string. But I want to support the semantics that this is some unique identifier. So I just tag a UID string. And that thing on the bottom is a representation of time, but it's represented as a string. And the way is I tag it as an instance. And so then when I pass it on to my system, it portrays certain semantics, right, that I want to support. And you can basically customize this to your domain. So then we come to flow, right? Flow is really simple to understand because all we want to make sure is that we have one-way data flows. So we have some set of data A, and we want it to get it to a set of data B, and we do that through some pure function f, some pure transformation. Or if you're more of a graphic person, it would look like this, right? The thing we're guaranteeing is that for all of A, there's a function f that will give us B, but the reverse is not necessarily true. And we don't care because we're only going to be doing these things in one direction. What I find really insightful and useful in practice is to start thinking about the data types and sort of ignoring the transformations. It turns out that this is really practical, this is really useful in practice. This is something that Haskell and Clojure has taught me because it has 2 nice properties. First of all, when you start talking about the data and not the transformations, you really start focusing on your domain, which is really useful because you have very important conversations with your colleagues about what it is that we're actually trying to model. And the other nice property of this approach is that for people who are not functional programmers, they get really excited about this idea of data transfer, of modeling data in our system. And without even realizing it, before it's too late, they're already functional programmers, right? They reach the conclusion on their own that the way to build these systems is through functional programming because they have already accepted that the way forward is to talk about these data transformations. Which brings us to the secret sauce. Our system is basically going to be a black box where we're going to introduce facts into our system. We're going to store it in some sort of a log. And then at some point in the future, we're going to ask it questions and it's going to give us answers. So let's talk about facts. I think Bruce Lee has a lot to teach us about system design. He once famously said, "You must be shapeless, formless like water. Water can drip and it can crash." I don't think he was realizing it at the time, but he was talking about flat data. Because flat data turns out to be just like water. It can take any shape you want in the system, which is a really useful property if we're talking about facts, things that are coming into our system. And to be more precise, I'm really interested in the following representation, EAVT, entity, attribute, value, time. It turns out that this is a really nice representation for facts coming into our system because A, it's flat, B, it can represent any kind of model we have, and lastly, it's understandable by everyone, right? Not just programmers, everyone. Because it models very closely the way we reason about the world, right? Entity is just identity. And identity is something that we all intuitively understand, but unless you're a philosophy major, you can't explain it to anyone. This table has an identity because as soon as I start talking about this table, everyone knows exactly what I'm talking about, right? We have things on the table, but somehow they're not part of the identity of the table. Somehow we can automatically differentiate between these things. This table also has certain attributes. It has a certain number of legs or it has a certain color, right? So it has attributes and values at a certain point in time. If in the future I paint this table a different color, the value of the color changes, but it changes at some time in the future. It doesn't change the fact that at this point in time, this was the color of the table. This is a really nice way to model our domains. But this is a way to model information at rest. It's not enough to portray communication, because communication is a protocol where you transfer information. In order to model this, we need to add one more variable. Now it's EAVT Boolean. The Boolean tells us whether we're learning or unlearning facts about our system. And this way, we can now communicate the change over time of information. So, if we want to look at this concretely, we have some identity, 1, in our system, and it happens to be name Bob. I arbitrarily chose to use integers for the entities, but it doesn't really matter. They're just some arbitrary thing in our system. And it turns out that this thing in our system that we're modeling is a person. And the only reason I know it's a person is because in my domain, I applied the semantics that things that have names are people, right? So this is something, these are the semantics I bring into the system. The model doesn't say anything about this. To be more precise, I learn about Bob at time 100, and to be even more pedantic, I learn about Bob at time 100. Now let's look at what a transaction would look like. We have two transactions here. At time 100, I learned that Bob likes cats, and at time 111, I learned that Bob likes dogs. If I ask the system at this point in time, somewhere between 100 and 111, what does Bob like? The system will tell me that Bob likes cats. But if I ask the system later what Bob likes, the system will tell me that Bob likes cats and dogs. Notice that it's a flat structure, but it can model collections. Now, what if we want to limit our data? What if we want to have a constraint that says Bob can only like one thing at a time? Well, it's really easy to model because it means that in that second transaction, we have to retract the information that Bob no longer likes cats, he only likes dogs. We can model both systems, both ways. This, of course, doesn't have to be manually done, because if you tell the system that there's a certain schema involved, then it can sort of do this automatically for you, right? That's just a technical detail. But inherently, this is the way the system works. There's one additional nice property, is that the values of things, the values of attributes, can be pointers to other entities. So this gives you a way to build graphs and build references. So here we learn of Bob and Mary, and we learn that Bob happens to like Mary at time 111, and much later in the future, it turns out that Mary also likes Bob. And one last thing I wanted to point out is the fact that this is a pointer to an entity. So if, for example, instead of using to, I can say name Mary, because this is some way of identifying some other entity in the system. EAVT. This is the way forward. Everything else that I'm going to show is based on this. So if there are any questions about this specific thing, now would be a good time to ask. Silence. Yes?
I didn't understand value and
Value or time?
okay.
So this says some entity 1. This is the attribute, and this is the value.
Okay.
And this is a certain point in time that's a transaction. Okay? So you can ask the system about information at a specific point in time. We don't lose any of the history. Okay?
What's the difference between logs and this representation?
Logs?
Yeah.
We're going to get to that, actually. So hold on with that. This is similar to event sourcing, but it's not exactly the same. Yes. Let's talk about logs. So logs are a separate part of the system, because that thing that I was talking about is just a representation of information. How we actually store this information is we store it in a log. And more specifically, we store it in an append-only log. There's two reasons for that. We want to model total order in the system. This is kind of, there's always the question of performance, and forget about it. It doesn't matter. Any business system you model, that's sort of related to reality, has to have total order. Because as soon as you break that law, things will always start working wrong. So you need to fight that urge to have distributed inputs into your system. You need to have a total order in your system. And there's ways to work around it where you can distribute the transactors and still have total order. But for the generic case, you always need to have an append-only log in order to have total order. And the other thing I really wanted to mention is, in our industry, we have a real problem with business data. For some reason, our source code is really important to us. We store it in an append-only Git repo. We back it up onto hundreds of laptops. We create static and dynamic analyzers to make sure that it's all correct and so forth. What do we do with our business data? We just throw it around, right? The most common case of business data is to store it in a mutating database with a last write wins strategy. We don't even know if there are other writes involved. Why do we do that? The business data is the life, like the life and blood of your company. Start treating it with respect. Which brings us to the last part of the system, which is no matter how cool it is to store things, if we can't get that information back out, then it's a useless system. At the abstract, it's very simple to create a system to do this, because basically, for any kind of question that we have about the system, we can just read the entire log and get the correct result that we want, because we have all of the facts. In practice, that's not practical, because certain kinds of queries are better optimized for certain kinds of indices and databases and so forth. The nice thing about this is that we can model this. We can model this reality. So we can build custom databases that are optimized for answering certain kinds of questions, but notice that the databases are always fed in one way from the log. So you can have the best of both worlds. You store all of your raw data in logs, and then you build custom databases to answer questions. And all these databases are in sync because they all have the same log as its input source. Okay? Fair enough? So let's talk about queries. But before we do, I wanted to take a little short road trip to the side. Who here can read and understand SQL? So even the people who didn't raise their hands, I assume they can. But who here can read data log? One person is like, which is a really good answer because this is why I decided to use data log for this presentation. Data log is basically as old as SQL, and not enough people know about it. And I want you to go and learn it. This, by the way, is not data log. This is the logo for DataScript, which is a data log engine implemented in JavaScript that runs in your browser. It's a really awesome tool. So let's talk about queries. One kind of query we often want to make in our system is auditing. Someone comes along and says, tell me everything that changed, who changed what, when, and why. Usually at this point, if we have like a standard SQL databases, we just go home and cry, right? Because we lost all that data. But here we get it for free because we have the log. If you want auditing, here, I'll just give you the entire log. You can have everything, right? So you get this one for free. Other kinds of questions we often ask our system is some kind of relational row query, right? So this is what's most common in your standard SQL database. It's the idea of I have some identity, and I have a bunch of attributes related to it. Give me all those attributes. Well, if you want to do this in a performant fashion, we need to build an index off of that log that indexes by EAVT, because that means that we have this ID, and we'll have all the values for it. So once we have this kind of index, we can see our first data log query. I'm going to go really slow on this one first. Notice that we say, given a database and some ID, notice that I pass in the database as a variable to my query. I'm looking for actor names and ages. So this is like select. And this is the where clause. The where clause says, find me an identity, some entity that has attribute actor name. And this is the semantics, where semantics come in. I semantically said that in my data set, actor name means that this is an actor, right? So whenever something is tagged with, has an attribute actor name, it means that it's an actor. And this is the name of that actor. And the second thing is that I also want his age. Now I want you to keep in mind two things. All of the variables have question marks. And in this case, these two variables are the same, so they match up. Data log is basically like Prolog. Anybody done Prolog before? Okay, so this is like Prolog. The idea is that you have a logical language and these things have to match. There's a constraint solver and it finds all the actors and gives it the same name and age and just returns a list of these things. Okay? So other kinds of queries is you want to do relational columns, right? And this is where our databases often usually fall down, because if you give a standard SQL database too much data, it can no longer do column data. It can't do like averages and counts and things like that, because it indexes things in the wrong way. So then usually what happens is you push it off to a data warehouse or some OLTP or something in that nature. But the essence of this is that we just need a different kind of index. We need an index that goes by AEVT. Because if we index things in this fashion, then we can, in an optimal way, say, given some database, find me all of the actor ages and give me the average. And because we've created this index that goes AEVT, we can do this in a very fast manner. Graphs. We often forget about this, but our business domain is mostly about graphs. And in order to do optimal queries on graphs, you need to be able to traverse forwards, which we already saw, but you also need to be able to traverse backwards. So we need another index. We need an AVET index, because this way, we're indexing the reverse relation. So when we have something like 1 likes 2, we want to be able to say quickly that 2 is this reference. So we want to be able to say, who likes Mary? So then you check the 2 likes 1, right? So you need to be able to just reverse the data. So here's an example of a query, a graph query, which says we have 2 actors. So given a database and 2 actors, find me the actor, first and second, that's A1 and A2. Then for the first actor, find me all the movies he's played in. And then for the second actor, find me all the movies that he's played in that match the first one. So this query says, find all of the actors that played in the same, find all the movies that these 2 actors played in, and just give me the title, right? I didn't want to include a longer a longer example of code, but this is really easy to extend to n edges. So it's really easy to do full graph traversals. Other kind of query we often want to do is search, as in a full text search, right? None of these indexes that I showed so far are good at full text searching. But it turns out we have the technology. We have inverted indexes that index by term to document, right? Things like Lucene and so forth. There's no reason why we can't just set up an additional database like a Lucene or Elasticsearch or something of that nature, feed the data from the log, and be able to, in an optimum fashion, query full text searches. So this says, given that database in a query, I want you to do a full text search on this database with a movie title query. Notice here, we are using the symbol identifier in an interesting way to tell us that this is some kind of operation. And then, so find all the movies titles based on this full text query, and just return the titles sorted by score. EAVT. I can go on and on and on. There's lots of other kinds of interesting indexes that you can build to answer interesting questions. But the point is that all of these things are possible just with this one simple data storage mechanism. And so that sort of comes to like the conclusion of the talks, and is in the sense, what do we get out of all this? Well, first of all, I want to point out one real thing that not a lot of people understand. In the real world, your application has at least 3 data structures that are constantly in motion. All of your data comes in some form of a stream. All of your UIs are some sort of a hierarchy tree structure. All of them, whether it's mobile, web, or whatever. No matter how you look at it, at the end of the day, it's a tree structure. And all of your business data is most likely a mesh. Most architectures don't take into account the fact that you're constantly working in 3 different dimensions. And you need to be able to, no matter what kind of architecture you decide to use, you need to think about this problem. Can I work in these 3 structures at once sensibly? I want to especially talk about mesh for a second, because it's something I sort of made up. Mesh is a graph, as far as I'm concerned, but it's a very peculiar kind of graph. I find that in most business domains, there's only a couple core objects to the domain, and everything else is metadata. For example, let's say you take Spotify, right? So core objects in Spotify could be, for example, you have listeners, artists, and songs, right? Artists write songs, listeners listen to songs. Well, what about playlists? Playlists are not a new object in our system. A playlist is a new relationship between a listener and a song. So it's a new edge with certain metadata attached to it. Similarly, if someone creates a playlist, then other people want to listen to it, they subscribe to it. A subscription is not a new object in our system. A subscription is a new edge between playlists and listeners that are subscribed to it with certain metadata attached to it. What you find over time is the amount of core objects of your domain do not change. So if you model them correctly, you'll be golden. What changes is that as you add product features and so forth, new relationships emerge between those existing things. So you need to be able to reliably model a mesh that's constantly growing and becoming more dense. What's the ROI on all of this? As far as I'm concerned, building systems in this kind of architecture, it turns out that they're a lot simpler to reason about, both for users and for developers. They are easier to make changes to, to adapt, and they're easier to test because all this one-way data flows has really nice properties for testing as well. I think this is one of maybe several legitimate solutions to how we can actually build complexity icebergs versus dependency icebergs. Now I want to leave you with some applied theory. Because this was all theory, the question is, how do you apply this in practice? I think we should all start focusing more on queues. I think we don't do enough. We don't think enough about queues in our system, because at the end of the day, your system is just a bunch of queues through which data passes. If you bring that out, if you make those first-class citizens, a lot of nice, interesting properties just fall out magically. I think we should all learn data log and declarative queries and query languages in general, but data log in specific. This is an awesome website, learndatalogtoday.org. It's going to take you about 2 to 3 hours with your favorite glass of scotch to learn all of data log. This is an interactive website where you can do queries to existing database. I think it was of either movies or songs, something like that. So yeah, seriously, if anyone tells me they can learn all of SQL in 3 hours, it's not going to happen. But you can learn all of data log in 3 hours at an easy pace. And Simulation property testing, generative property testing. I think we don't do enough of this. I think we need, as an industry, we need to do more of this. And it turns out that if you think about this ahead of time, you start building systems in different ways. Because you start building systems that are easier to test in this way, right? If you want to look at practical examples of how people are doing this in industry, check out, for example, Lambda architecture, if you're interested on the macro level, right? So Lambda architecture is this architecture applied at a macro level of the entire system, the entire backend system. So things like LinkedIn, and LinkedIn, for example, is really known for Lambda architecture, right? So these things are being done in industry. Check out Martin Kleppmann's talks and content. He does a lot about, he gives a lot of information about SAMSA and inverted databases and so forth. So basically, a lot of the same ideas applied at a database level. Similarly, Datomic. Study Datomic architecture, because Datomic thought really, the guys behind Datomic thought really long and hard about how to build these systems. They were really, a key insight was the fact that they separated transactors, storages, and distributed peers. And they actually used this kind of EAVT protocol as a protocol for synchronization of these separate things. If you're more interested in the client side, I really recommend you check out OhmNext. It's not even released yet, but they already have a lot of good videos and other content, blog posts and so forth about the architecture behind it and how to build applications using this kind of approach. And just one last thing, if there's any PhD students in the audience, I really recommend, I really think CRDTs are the future. I think, among other things, CRDTs might be the answer to how we can build, how we can have multiple transactors and still have total order in our system. So I think this is a really interesting research direction. I think there's actually a talk this today, right, about CRDTs. That's the end of my talk. Thank you for being such a wonderful audience.